This is a video on conservative forces and non-conservative forces. Let's say you got to push a boulder up a hill. If the work that's being done is not dependent on the path you take, it's a conservative force. What does that mean? Well, you could take a path like this, or you could zigzag up the hill. But if the total net work at the end of everything is the same no matter the path you take, it's a conservative force. Another key identifier of a conservative force is if you go from the starting position to the finished position, and then you go back to the starting position, if the net work is equal to 0, it's a conservative force. So to sum it up, only the initial position and the final position matter. It does not matter how you get there and how you get back. However, if it does matter, if the way something gets to its second position does change the amount of work being done, then it's a non-conservative force. In what situation would that happen? Let me give you one. Let's say you have a room, and inside of this room, you have to push this chair, and you got to push it all the way over here. The shortest path, which is this, and we'll label this as path 1, and this is the path you take if you want to do the least amount of work possible. But if you were to push the chair in a path like this, or you spiral around and you zigzag and all that, then the total amount of work that friction is doing against your pushing is more, because friction is always being applied, and things like air resistance as well. So that means the work being done by forces like friction, air resistance, whatever else is opposing your motion, these forces are non-conservative, because the amount of work being done by these forces is dependent on the path you take. So you know that air resistance and friction are non-conservative forces. Let me give you a little quiz. Is the force of a person pushing something, is this a conservative or non-conservative force? This force would be non-conservative, because if you wanted to push something from one place to another place, then the path you take definitely matters when it comes to the amount of work that the person's doing. Now, how about an elastic force? Is an elastic force conservative or is it non-conservative? An elastic force is actually conservative, and here's why. If you had a spring like this and you pushed it down, when it bounces back up to its resting state, so it goes down and then back up, the net work being done would be 0. So by definition, it's a conservative force. Let's define the total mechanical energy in a system as E, and the total mechanical energy is equal to all of the kinetic energy plus all of the potential energy at any given moment. This is assuming that there is no non-conservational forces acting in this system. So no friction, no air, nothing. All of the energy is conserved. Because let's say we did consider friction in this system, then some of your kinetic energy and your potential energy would be turned into heat, thermal energy. And that would mean that the system is not conserved. So if you're a tiny bit confused, just keep following along, it's going to make sense. Since E is equal to kinetic energy plus potential energy at any moment in time, then that means the sum of these two energies at one point in time is going to be equal to the sum of these energies at a second point in time. This means that E1 would be equal to E2, which means that E is constant. Of course, only when non-conservational energies are doing 0 work. What does this mean? Well, because we have this much mechanical energy initially, then at some time later, which we'll call E2, E2 would have the same amount of energy as the initial energy, which means that it's a loop, it's conservative. Just like how when you're moving something up a hill, in a conservative energy system, where there's no friction, no air resistance, nothing, then if you were to move from the start to the end and back to the start, you would have done 0 net work. It's a loop. And this right here is a beautiful, very, very simple relation between conserved mechanical energy and the energy working in a system. And we can use this equation as a formula to solve problems. Here's another useful concept to know and have in your brain. In a conservational system, just like the one that we explored 5 seconds ago, the work being done by non-conservational forces would be equal to 0. And the work being done by non-conservational forces is the change in kinetic energy plus the change in potential energy. So things like friction, air resistance, the push of a person, it's doing 0 work on anything. If you rearrange and you subtract kinetic energy, then you get the change in potential energy is equal to negative kinetic energy. This means that as kinetic energy goes up, potential energy goes down. And as potential energy goes up, kinetic energy goes down. And this is very useful in a lot of scenarios. The equation that we explored earlier, which is E equals KE plus PE. Oftentimes, it's easier to use this than to use Newton's laws or the kinematic equations. It's easier when a problem involves the conservation of energy, which means that the total energy in the system doesn't decrease or increase. So no energy is lost, no external force gives energy to the system. Now this was some pretty theoretical stuff, but to actually understand what it means, in the next video, I'm going to do a bunch of problem solving with this specific concept. For every topic I cover, I like to create a free cheat sheet, and I use them myself as well. So if you want your own with all the formulas you'll ever need in one place, then go sign up in the description.